time to talk to Martin Cooper, formerly with Motorola. So that was a very nice time. So I can share the memory about him with you in the future when we see each other. And I had to take a step inside of the handset. Actually, most of these structures are being prototyped. Though there are some commercially successful or commercial equipment which are available, but mostly in the advanced countries, technologically advanced countries, or who proposed 5G first, much ahead of us. So, but you can see you can take a peek on antennas, but the antennas, the shapes are not much different from what we have learned from the textbooks on antenna engineering. But as the technology evolves, the antenna is more intactly connected with the systems or system operators. So, but with radiators, radiating elements, and 2x4 especially, 2x4 radiating elements are where you can see multiple 2x4 array antennas are placed here and there. Two of them occupy the corners of the handset platform, but this is not the perfect picture. Actually, this was taken in the process of being prototyped. So you can they try to look at the proper positions of the antennas to get to satisfy the industrial requirements on fast data transmission under the name of 5G. And also you can see 1, 2, 3, 4, 2x4 antennas, cavity-backed antennas, which are directly connected to the chip. So the chip is feeding the millimeter wave energy to the individual elements of the radiating structure. And also you can see what Ericsson's 5G radio prototypes for live field trials. This is what not only case what you can see, and you can survey a variety of equipment antennas which are available or being tested. So before talking the application fields of the metamaterials, I have to talk about what metamaterials are, but you already know. But the picture I took from last InCap, this picture was very beautiful. As you can see the background picture of the three dancers. These pictures can be a proper pattern for a metamaterial if they are tuned to your own taste. So when I was attracted to these patterns, I had to take a picture, and I wanted to share this with you. And I have a gallery of the pictures that can represent what metamaterials are. Especially, you can focus on the pictures on the first row. You can see that. You can see them. If we talk about, if we want to design a metamaterial, the effective epsilon and the effective mu should be less than 1 or negative. So both epsilon and mu are negative. We call it a double negative material, which takes us to the negative refractive angle. So the first picture is talking about when there's an incident wave which touches the interface between the right-handed material or double positive material and double negative material. The refraction angle becomes negative, but the wave front, the phase is reverse or opposite to the direction of the energy propagation. So that's the first picture of the first row. The second picture is the dispersion curve. So you can derive or extract the dispersion curve, which tells you before talking about that, dispersion curve is the relationship between phase and the frequency. So you can see two different regions. LH here stands for left-handed or double negative region, and RH stands for right-handed region. So this is ordinary, what we can experience with the Teflon material or what epoxy or others. So when we see these two different regions existing together in the metamaterial, right in between these two regions, there's a ZOR, or zeroth order resonance mode, which can be also usefully utilized for some applications. And the third picture in the first row is the electric field distribution of a metamaterial circuit, which is the bandpass filter. But not only bandpass filters or circuits, but also I design with my students metamaterial antennas or lenses. But when you see this type of picture, you might be wondering what metamaterial property regarding zeroth order resonance means. This tells you, so from on the left-hand side, that's the port 1. On the right-hand side, that is a port 2. Energy is injected to port 1. It is flowing, and when it is well designed to pass the signal, it reaches the port 2. So while it propagates from port 1 and port 2, actually there's no phase difference when you can tune the frequency of interest to the zeroth order resonance. So this is the third order bandpass filter from stage number 1 up to stage number 3. You can see the same colored electric field distribution. So this tells you what zeroth order resonance means. And last thing last in the first row is sub-wavelength size. So you can compare two different filters for the same purpose. You can see just kind of a very thin red line. Actually, this is the kind of a shrunken picture of a third order edge couple filter. But for the same frequency, you can reduce the size of the filter to a rectangular one. You can see below the red thin line, there is a filter, but you can see it clearly, but you can compare.
Sir, excuse me, sir. This PPT is not clear visible, sir, because due to this small size. Can you zoom
yeah,
in?
yeah. And, let me see. But the resolution is not good. Resolution is not good. So
Okay.
yeah. Well, when there's a supplementary picture, I'll bring it for you at the later section. So anyway, I can reduce the size compared to the conventional bandpass filter or just microwave circuit design technologies. The size is less than 1/8 or 1/10 of the conventional structures. So what actually you can add more properties to these four representative properties of the metamaterial, but I can summarize the metamaterial properties into these four kinds. So negative refractive angle, if you design your structure with the double negativity, and the dispersion curve tells you where your antenna or your circuit is working in terms of the frequency and the electric field distribution. If you want to design the negative beta or negative wave number structure, the wave, actually the phase moves from port 2 to port 1, while the energy moves from port 1 to port 2, like that. And also homogeneity. Homogeneity tells us the size of the metamaterial unit cell should be less than lambda over 10 or lambda over 20, theoretically. That's all. So, and below the first row, you can see a variety of applications of the structures, but this picture is image picture. If I try to zoom from one picture to one picture. Each of these pictures, actually, the resolutions are not good. So please bear it for me. And let me move on to the next. And you have seen the early works on metamaterials. So I took these pictures from the Pendry's work and Smith's work and Schultz's work. You can see the representative structures which introduce us to a negative mu SRR and a negative epsilon with the metallic rods periodically or non-periodically arrayed metallic rods, which introduce us to the negative epsilon. So if you put these different structures together, we can experience from the standpoint of the dispersion curve or beta becomes negative. Beta becomes negative. So underneath these pictures, you can see the formulas to one model the electromagnetic behavior of the SRRs and the periodic metallic rods with the Lorentzian curves. But what Drude or Debye models can be used, especially for epsilon negative materials. And right at the center, you can see 4 quadrants, especially the gray areas. There are 2 gray areas. The first quadrant is one of the 2 gray areas. This means the double positivity or double positive material as the energy is moving from the source to the distance or the position of the observer, the phase or the wave number goes along with that. Well, this is what typical thing we experience in the right-handed material. But the third quadrant tells us the energy moves from the source to the observer. That's the direction, normal direction of the energy propagation, but phase actually is moving backward. So it is called also backward wave propagation. This occurs from epsilon negative and mu negative. This is what Veselago found many decades ago, theoretically, but Pendry and his group at the earlier days of metamaterials, they came up with the SRRs and the metallic rods to show the negative refraction, refractive index. So you can see a very interesting pair of pictures. We designed a metamaterial transmission line. Actually, this works as a bandpass filter. Somebody already has seen this last year when I was giving a talk. And for the same structure, what in the left-hand side region, especially in terms of the frequency, below the 0th order resonance frequency, what the top left picture tells you, energy is injected to the left. There's a bottom. The curved transmission line is confined in the blue rectangle. So the lower edge or bottom edge of the blue rectangle has port 1 on the left-hand side and the port 2 on the right-hand side. The energy is given to the input port, which is located on the left-hand side, but energy is injected from port 1 to the port 2, but this is the phase, this is the phase of the electric field, which moves from port 2 to port 1. So this occurs at the left-hand side frequency as we planned. Otherwise, or on the other hand, on the right-hand side, the same structure shows you the right-hand side propagation from port 1, which is located on the left-hand side, and it goes along the flows on the transmission line and touches that reaches the port 2. This is what happens in the right-hand region. So if you take a look at the dispersion curves, which are called just a pure right-hand side and a pure left-hand side dispersion curves. When you put them together, it is called the CRLH, that is composite right and left-hand side. So what on the right-hand side, there are two pictures. The blue part of the blue part corresponds to the left-hand side, left-handed region or beta negative, but at the same time, the red part corresponds to the beta positive or right-handed transmission region. You can connect the blue beta negative curve and beta positive, the red curve together. When the two points are not connected, it is called the unbalanced condition of a metamaterial CRLH. But if you put these different frequency points together to make one zeroth order resonance point, it is called the balanced case of a CRLH. Just for your info, you can see Professor Ito and Professor Gallo's textbook. This comes from their books, but we had to draw the dispersion curves on our own. Let me move on. And you can see another kinds of metamaterial properties. So the left-hand side, sorry, left bottom is the wavefront, which experiences the double negativity when the energy is coming right out of the horn antenna on the leftmost region. It is propagating and touching the, you can see the intermediate region, which is the n equal to -1 or negative refractive index slab. There, the energy is flowing, but the wavefront moves backward. But actually, energy itself reaches the right end of the intermediate region slab, and it is propagating to the rightmost region, which is air again. So the composition of these regions is air, negative material, and air. So you can see the negative refractive index, or negative refraction angle. So incident wave is impinging with the positive angle of incidence, but it turns into the negative in the n equal to -1 material, and it turns back to the opposite signum again in the air. Yeah, that's what we can experience in the transmitting case. But on the as another example, we designed metamaterial bandpass filter, which is different from what I already told you or elaborated on. This tells you, you can see there's a three-dimensional box. Yeah, so left-hand side, it is the number 1 is given there. This means the port 1 region. And on the other side, you can see number 2, which is given as the port number 2. The energy starts from port 1, but and it reaches port 2 without any problem. Actually, if we take a look at S21 as the transmission coefficient, there's almost no insertion loss. So the frequency of interest has the pass band. So in the pass band, we can make a pass band in the left-hand side region, or we can make a pass band in the right-hand side region, or right in between these two regions, say for example, ZOR or zeroth order resonance, we can make a pass band too. Anyway, we make a pass band in the left-hand side of the this metamaterial circuit. So you can see the electric field moves from port 2, port 1. This is the wavefront, but energy reaches number 2. So this is not a trick. Actually, this is what we got directly from the simulator we have used to design the structures for telecommunication systems. Let me move on. Yeah. So with the help of CST of Korea, now it has been absorbed into Dassault, the multinational company. Anyway, we worked together for giving lectures on metamaterials many years ago. So you can see the structures, which is the half of the prism, this prism, and this prism is copied into and repeated into the bottom. And when they are put together, then it looks like kind of lens. So the first example means what negative refraction angle occurs with the first picture when epsilon and mu, the material is designed as the epsilon negative and the mu negative. At the same time, if you make another prism and the prism on the left-hand side is copied to the bottom, and this becomes a kind of a focusing structure, but what it should have been tuned further to have a sophisticated function. But this was designed to just test how the negative refraction angle works in terms of what the focal point making structure, at the same time the beam bender. And last time I visited what IITs, I introduced this picture. What you can see, Sugata Chatterjee, who works for National Center for Radio Astrophysics, sponsored by Tata Institute of Fundamental Research. Yeah, they mentioned my papers, and the structures are quite similar to what I have designed before. So this structure on your left-hand side, there's a blue box, or what the contents with the blue frame. This structure was already proposed many years ago. This is a kind of one of the first works, the bandpass filters working at the zeroth order resonance, which could be helpful in reducing the size of the structure as well as the good insertion loss performance. So thanks to them, well, I could see what the extension of my bandpass filter or metamaterial filter is used. Let me move on. And the metamaterials can be also used to stop the interference between the two antennas. So as you see, two dipole antennas on your left-hand side, especially left top, two dipole antennas, they are put very close together in parallel. Then the interference is the highest, but you can stop the interference between these two antennas by putting the band stop type metamaterials. You can see on the right-hand side, you can see a periodic structure which is embedded right in between the two dipoles. Then you can increase the isolation. So isolation level here is the red curve. Then the two dipole antennas work almost independent of each other, even though they are located in the vicinity of each other. And also on the bottom, center bottom, you can see my absorber, which works for the frequency starting from almost 6.2 gigahertz up to 15 gigahertz. And there are many metamaterial absorbers introduced by Indian research groups. So I'm really enjoying seeing them. And by the way, yeah, I have to move on to the metamaterial circuits and antennas for 5G systems. So beamforming, actually last year in INCAP, well, there was a series of performances. I really enjoyed that, and also took the pictures, the light beam, you can see the beams. So we want to make the beam from the antenna at the same time, or further, you want to steer the beam too. So we have designed the reference antenna on our left-hand side, but with the help of a metamaterials technology, we could decrease the footprint of the Butler matrix to which is fit for the inside of the handset device, by keeping the number of the beams we want to. And also, you can see the planar layer PCB Butler matrix can be reduced. Its size can be remarkably reduced to the smaller one. You can see on the picture on your top left, well, two structures are compared together. So using the CRLH concept, and also you can see the field distribution, the animation of the field distribution on the left bottom. When it is the one port is turned on, the energy is propagating from there to the output. And on your right bottom, there are 4 pictures which tells us the beam steering is possible. And my student was inspired by the 2D beam forming structure. So without using the very complicated waveguide structure, he changed it into very simple metamaterial type 2x2 beam steering antenna. You can see at the center and on the right hand side, the beam is shooting the antenna is shooting the beam to the 2D space. And we could reduce the size of the SIW Butler matrix from the biggest one to the, there are 2 more versions, but which have not been put into this slide. But the 8x8 Butler matrix can not be accommodated to the handset device. So by using the metamaterial feed network, which is hidden by the top surface, so we could make the antenna much smaller than the original one. So you can see the 8 beams, they are distinct from each other. And the 4x4 Butler matrix, which can coexist with the my LTE antenna. So as you see, from frequency, from 5G to LTE, actually the frequencies are very away from each other. But these structures, as you see on the top left, the 28 gigahertz antenna, radiating elements and the feeding network is quite close to the 4x4 MIMO antenna. So the purpose is to isolate these antennas or decouple the electromagnetic coupling between different structures from corner to corner. And this antenna is very robust, which is not affected or vulnerable to the hand grip. And you can see the beams which are made for the 28 gigahertz. And also, you can see what very low frequency working sensors, which work at 433 gigahertz, which is very low compared to the 28 gigahertz, such as keyless car, you need 433 megahertz. So these antennas, these different antenna systems do not interfere that much. So as you see, at the center, the bottom, and the right hand side, the bottom, one antenna, 433 megahertz antenna is working. This antenna doesn't affect the performance of the 28 gigahertz and the other 433 megahertz antenna sensor. And also, we could make just metamaterial beamforming antenna, which was used to deliver the power, which is called wireless power transfer, funded by the Korean Institute. So there we could make just 5 beams, or we could increase the number of the beams with the help of the metamaterials. And this work is still going on because the number of the elements is too large. So the simulation itself is very, very challenging. But we can increase the antennas, and the antennas, you can stack them, though you can stack the antennas just on the top of each other. These antennas do not interfere with each other. in the far field, they interfere for beam shaping. And this is the poster, which includes the metamaterials. Where metamaterials are applied to, but I'm going to skip this. And until this time, you saw a metamaterial which works for different purposes, and you can see another set of examples too. So lenses. So you can see the fibropearl cavity, but a fibropearl cavity which goes with which can go with the frequency selective surface, but we had to make the fibropearl cavity with the help of N, or refractive index, almost or exactly equal to 0. So you can see a picture at the bottom. The center tells us this is the plot of complex negative refractive index. So the frequency we were interested in was around 10 gigahertz. It's a KU, or it belongs to the end of the X band. For satellite communication, we had to make the fibropearl lens with the help of a metamaterial concept, and almost equal to or equal to 0 at 10 gigahertz. So on your right-hand side, rightmost side, you can see the beam, the directivity is much improved by the conventional structure. And also you can see the metamaterial surface, which shows us the negative refractive index, as well as the the twisting of the polarization. So left-hand side, this picture is the animation of the electric field, which electromagnetic field, which experiences the this tilting or inclination of the angle of transmission. But you can just change the shape of the unit cell to just a diamond shape, which is inclined a little bit. Then you can make a circular polarized wave with high directivity. So you can do both. And my students and I, sponsored by the ETRI in Korea as the National Institute, we could make a fibropearl cavity along with the metamaterial structure. And you can see the metamaterial unit cell, which looks like just a clover shape, loop clover shape. And by changing the size of the unit cell and the shape, and you can make a high directive antenna. And also underneath the primary antenna, which hits the, shines the EM wave to the bottom of the superstrate, that is also minus first resonance mode antenna, and this is incorporated with the circular polarization and n equal to 0 metasurface, which changes the just low gain antenna beam to the high gain antenna beam. And also you can make a metasurface which consists of as you see, there's a thick or fat just crosses. So this periodical structure is put on the top of the cover of some kind of radome. The antenna, which has the beam which is degraded with the obstacle such as a radome, but you can put the periodic crosses on top of the cover. You can change the story. And one guy from Sony in Sweden introduced our structure, which was aimed at changing the low gain beam to a high gain. So the 1x4 antenna changes to 2x4 or 1x8 antenna beam. So we can do that too. And also, when there's a radome which is quite close to you, the original antenna, the beam performance is going to be degraded. So by adding a different type of meta surfaces on the radome, then you can increase the gain as well as the good impedance match. So underneath at the bottom, you can compare 3 different wavefronts at the center is the beam, which is a deteriorated case due to the obstacles such as the radon. But on the left-hand side, the original antenna beam is retrieved by the Metasurface, which is printed on the radon cover. So on the right at the center, you can see the finalized beam. And we also tested the Metasurface, which is the kind of a reflector array for UHF. Before us, most of the metamaterials, especially reflector arrays or transmit arrays, were used with the Ku band or Ka band, such as 28 gigahertz or around 20 gigahertz. But we wanted to test the Metasurface can work for even UHF. So we could increase. Well, you can see the small antenna. It looks like an RFID antenna, which works at the 920 megahertz, whose gain is 1.6 dBi. But if you put the reflector array behind that, the structure doesn't have to be that very enormous. The size is quite reasonable. Then the space between the small antenna and the reflecting surface is less than lambda over 4. Can you believe that? So there you can change the gain of the antenna. So 8 dBi was what I obtained. So this is the effect we can get with the 1x4 array antenna. So not using the 1x4 array antenna, just by introducing the Metasurface, we can change the directivity or gain of the antenna from low to high. And reflector array, but this is what you can also hinted by other reflector array antenna designers. So I'll skip this, but we could also enjoy that technology too. Would increase the gain of the horn antenna to a larger one. And this is just another test with the, instead of the horn antenna, it's Vivaldi antenna. And we move on to another topic, and the dense and MIMO antennas. So you can refer to my papers, which are related to the MIMO, which had to increase the density of antennas that are placed in the platform of the mobile phone. We were funded by the LG Electronics many years ago, and the project went on for many years. So we started from the 2x2 MIMO, where you can see the two zeroth order resonant antennas put together in the vicinity of each other, and also the isolation higher than the other antennas. And we could increase the bandwidth, or we could extend the work from the very low, a narrow band to the wider band. So LG people then were very much happy with the achievement. So though the antennas are quite close together, and antennas are already very small, smaller than lambda over 8 or lambda over 10, but the gain is we didn't have to pay for the price of small structure. The beam was quite good, larger than 0 dBi or just below 0 dBi, and the isolation level was also quite plausible. And another 2x2 antennas, and these 2x2 MIMO antennas had to be with another pair of 2x2 MIMO antennas. So this was a new kind of test back then. And we could put 8 antennas on the like a palm-sized platform. So you can see 2 cases of 0th order resonant antennas. So the top, it is electrically driven or electrically coupled 0th order resonance antennas, and the bottom is the 8x8 magnetically coupled 0th order resonance. But this coupling here means the coupling for exciting the radiating structure not for interfering with others. So isolation level is, as you see, 10 dBs, even though the space between the neighboring elements is less than lambda over 10. So Korean Advanced Institute of Technology funded for this work for more than 3 years, so they could get a success to replace a big panel of densely populated monopole antennas. So just they replace it with mine. And also dual band metamaterial feed network, which gives you two types of beamforming schemes. So for the low frequency, such as 2.4 gigahertz, and for the high frequency, such as 5.2 gigahertz, only one structure could give two beam schemes, beamforming and beam steering schemes. That was possible. And also we could make 16 different cases of beams by having MIMO array. MIMO and array are different topics, but I had to combine the MIMO or densely populated antennas together with the array antenna, which should interfere, whose electromagnetic wave or fields are interfered in the far field. So as you can see, all those 8 and 16 cases of antennas have a good return loss at the same time, good isolation, and the beams, even though they are plotted in the by the EM software simulation software, we could test them without any problem. And also we could go further to make 4x4 and 8x8 MIMO antennas for handsets. So this was the first test and first try ever reported. What Taiwanese professors could put 4 and up to 8 antennas in the handset, but they do not have the beam forming and beam steering functions. All the antennas should work independent of each other, but we could use these antennas as MIMO independent antennas, as well as we can use them as beamforming antennas too. So Samsung Electronics was really interested in several years back, but what we are just enjoying what we had. Anyway, we could go to the different experiment where we make an electromagnetic band gap, which is called EBG, to increase the isolation between the neighboring 28 gigahertz antennas, as you see. So on the left-hand side, that is top to bottom picture, and the two antennas are located vertically, but these two antennas are extended to kind of 2x2 antennas. So we can increase the isolation by designing the Metasurface underneath of the radiating elements like that. And also my student could design two dual band monopole antennas, and at the same time he could also design. You can see this arrow. This is a before and after picture. This tells us one isolation structure, because it is being filed for a patent. We couldn't reveal the structure for you. Later, you can see them. So 2.4 gigahertz and the 5.2 gigahertz, you can see the isolation, which has been improved by the intermediate structure. And you can see the distance between the two antennas is 32 millimeters, just for your reference. And metamaterial circuits and antennas for 5G systems. Again, now we are going to tap into EMC problem. So antennas, the fields of antennas, circuits, and EMC cannot be separable in telecommunication area. So by having good EMC performance, you can make good antennas like that. So when I was invited by Samsung Electronics, they wanted to make their antenna very robust against the electromagnetic interference from layer by layer. So if you open a book of EMC, especially signal integrity area, the signal integrity area, you can see what RFIC, which is connected to the radiating element, it's a long journey. You can see a bending of the line and the vias which surround the transmission line. This can cause resonances. So the resonance can cause the problems. The resonance between the two parallel plates can trap the energy. This energy cannot reach the radiating element. So you should remove the resonance at the frequency of interest. So what I'm showing you is if you have a unwanted or spurious resonance by the parallel plates, which occurs from the layers of chipset antenna, or that is called on-chip antenna, you should remove the resonance by putting some kind of EMC player. So eye diagram is very bad when you have unwanted resonances between the two plates, and the return loss is very poor in terms of the antenna, and the radiation patterns are very poor too. But if you give the Metasurface filter right in between the two parallel plates, actually this one, you can see the black curve here. Black curve is the return loss. So at the 28 gigahertz, the return loss drops. So S11 drops. So that means energy can flow through the parallel plates. Then the energy all the way from the pin of the chip can reach the element, and the one patch antenna, which is located on the top of the RFIC antenna, it has a typically sound and healthy radiation field. And eye diagram is also very, very clear. We have a good opening of the eye diagram, and return loss here at the 28 gigahertz is very good too. So you can extend the RFIC antenna by having the metamaterial surface device. Then you can make this beamforming structure like this. This is what I gave a consultancy on for Samsung Electronics several years ago. And recently we published a paper which tells us the channel selectivity of a 3.5 gigahertz. This is a kind of a systematic approach, and pull the bull by the horn kind of approach. As you see, 3.5 gigahertz area, 28 gigahertz area, we can also test the channel by channel selectivity, from channel to channel selectivity. Selectivity here means 3.5 gigahertz consists of 3 bands according to the frequency plan of the Korean government. Maybe this works for other countries too. 28 gigahertz also. In Korea, we have 3 mobile service network providers. So likewise, 28 gigahertz in the region of 3.5 gigahertz, sub 6 gigahertz area, we have 3 frequency channels. So by adding metamaterial filter and the metamaterial multiplexer, which is used as the feed structure for antenna, wideband antenna. So the structures, if you read my paper, you can see what I'm trying to tell you. But underneath, you can see the 3 pictures. If I select the channel 1, the red curve tells us, oh, the receiver side energy around minus 40 dBs, but which is pronounced compared to the rest of the bands, is picked up. And if you change band number 1 to band number 2, number 2 band is selected as the center picture, and the rightmost picture tells us the channel number 3 is selected, the corresponding frequency. At the corresponding frequency, you have the peak of the reception or receiving power. So let me conclude. Yeah, because I have been here so far, and thanks for your patience to see and hear what I'm telling you and delivering the message of the profits we can get from the metamaterials. Actually, you can use your own, or you can come up with your own ideas to tackle the problems given by the industry or on your own. And whenever you need my consultancy or advice, my door is open to you. Thank you.
Okay. I see there are so many questions from the audience.
Yeah.
Yeah.
Let me check.
One by one question from
Yeah,
the
yeah.
audience. Yeah.
Mm-hmm.
The first question, is there any negative refractive index material found in nature?
But in nature, negative materials?
Yeah.
Well, maybe, but I haven't done research about the natural metamaterials. But there already exist chiral materials, and because the molecules and the materials consisting of crystals may be dependent upon some periodical periodic structures can make some bizarre effect. Maybe that can be metamaterial concept or birefringent structures. Some people categorize it into metamaterials, but mostly man-made by mistake or by design. They are metamaterials, but that's my interpretation.
Okay, thank you. Next question is, does absorption means transmission and reflection coefficient being mean simultaneously?
Reflection and transmission can be minimum simultaneously, right? That's the question?
That's the question.
Yeah. Then absorbers can be the right answer. Absorbers. Yeah, absorbers, reflection coefficient should be as minimum as possible. At the same time, transmission should be transmission inside of the absorber should be high, but behind the transmission, the absorber structure, the transmission should be zero or very small. That which is the purpose of absorber. But there are no perfect absorbers anyway.
Get index metamaterial, why waves are each other and disappear? Is there any violation of law of energy?
Let me see. No. So loss of energy. So Professor Yadav, just say that again, please. Read that question again.
Yeah. In negative index material, why collide with each other and disappear? Is there any violation of law of energy?
Yeah, it was quite controversial back in 2002 or up to 2006. Really, the energy disappears, but it is not true. It is not true. Energy go around somewhere else. You can bend it or you can take it to somewhere else. Yeah.
Okay, so is there any effect on the side lobe of antenna by placing metamaterial in between?
Sure, definitely. So, if especially the side lobe or unwanted lobes will occur when you put separately designed metasurface and source antenna together at the first stage or right after the combination of the separately designed structures, you can see a lot of side lobes or unwanted back lobes like that. Even main lobe is not distinguishable sometimes. So putting them together, you should tune it again, over and over again. to kill the side lobes or minor lobes.
So next question is how the wave propagation differs when metamaterial surface is used as substrate or back reflector substrate.
Let me see. Please read that again.
Yeah, how the wave propagation differs when material surface is used as substrate or back reflector substrate.
Can I see the text there? Can I see the text? Oh,
yeah, in the box. I'm putting you directly on the chat box.
Yeah. Professor Adab, you are copying the question to the latest. No, the where I can see. No, this is yeah, right. How the wave propagation differs when metamaterial surface is used as superstrate or back reflector surface. How the wave propagation? Yeah. Metamaterial surface is used as superstrate or back reflection surface. What wave propagation? What? Let me tell you this way. What if you want to design a reflector array or back reflector surface? Most people rely on the metal backing. So the reflector array is backed by the metallic ground. So this guarantees the reflection back to where the energy started from. So without but I do not mean you all the time have to resort to the metal backing. No. But sometimes the metasurfaces of superstrate and those of reflector array look alike. So dependent upon your final objectives, yeah. But sometimes they look very similar, or sometimes they do not look similar. Is that okay?
Yeah. Okay, so next question is how the wave propagation differs when metamaterial surface is used as substrate, back reflector substrate.
Read that, please. Again.
How the propagation differs when metamaterial surface is used as a superstrate or back reflector substrate.
There's a kind of a difficulty in understanding
Okay.
what she or he asks me. Yeah. But my former explanation, the locations of metasurface are different, but that's quite clear. Yeah, superstrate is kind of right in front of the source antenna, but reflect array or back reflecting surface is just behind or below the radiating source. As far as you use as far as you design the reflector surface, then you should check the energy just propagating to the surface and reflecting back. But superstrate just one way, but the reflector array has just going there and reflected back. So you should check the two paths together, and that's how the propagation differs between the superstrate case and reflector array case. Am I answering right?
In
Yes,
Kahng,
yes.
sir, in one of your designs, you have used prism structure, which you made collaboration with CST of Korea. In that, how many metamaterial chunks you have used?
How many unit cells?
Yeah, sir, exactly.
Yeah. Too many to count right now, but more than 30 or something. But actually, the number 30 is not enough because the focal point is generated just above the boundary of the lens, the curved, just a concave lens. So to increase the focal length from the physical surface of the metasurface, maybe we needed more.
Okay, sir. Next question is, which is better approach? Either unit cell or separately or then embedded with antenna?
Could you say that again?
Yeah, which is the better approach? Either study the unit cell separately or embedded with the antenna.
Yeah. Well, not just for writing a paper or journal paper, actually, both ways are important. I mean, separate design should be taken first at the first stage of the design. The unicell as a periodic structure on your left-hand side, at the same time, antenna with the initial form of the periodic unicell-based metasurface together, but you will spend more time in the later part. But I think it is worthwhile to see the pure behaviors or the characteristics of the unicells first, just as using the plane wave test. So this tells you the reference or the direction. So unicell, because it is helpful to decide the shape of or the size of the unicell by checking the refractive angle of refraction, or S11 and 21 in the waveguide box, which is used for plane wave test. And then after getting the bearings or the directions from the unicell design or separate design of a unicell, and then you can put them together and adjust the gap between the surface and the radiating antenna together.
Okay, so next question is, which structures are called metasurfaces? How we decide?
Yeah, great question. Yeah. As I displayed the 4 pictures in the as the first row of my the gallery of the prototypes, yeah, metamaterial. Well, not all the periodic structures are metamaterials. You know a vast area of frequency selective surface, summarized or elaborated on by Professor Ben E. Munk from the Ohio State University, or Raju Mitra. Yeah, these people with their students or colleagues already introduced the fields of FSS. So you can get a hint from the typical shapes for the unicell when you design the unicells. But metamaterials, actually, you can check the negative refractive index or negative epsilon or negative mu, like that. Then you are convinced, oh, this is a metamaterial like that.
Okay, the next question is, if we reduce the size, what is the effect of interference between adjacent components? Because if interference increases, then it will be a bad choice. Can you elaborate?
Yeah. Correct. Yeah. Yeah. Well, there's no such no. But yeah, we all the time have in mind the interference between the adjacent structures when we have to put them together considering the just a limited space of a handset or some platform, then some people have used the orthogonal directions of the currents or orthogonal directions of the polarizations like that to minimize the interference between the neighboring elements. I actually adopt this type of idea sometimes, but not all the times. So the so independent or individual element, such as a ZOR antenna, should be as small as possible, and at the same time, when you have a good zeroth order resonance, which has the good near field electric field distribution concentrated on one structure, which will finally give you the good gain. Then, because the structures physically are already small and the distance relatively a distance between these two neighboring elements is already far away from each other compared to the conventional technologies. So that's how you can increase the isolation between the two antennas. So my suggestion is try to make as small as possible the individual antenna first, which has a good performance. And you can put the isolation or decoupling structures too.
Okay, so next question is, what dispersion diagram signifies in terms of different millimeter links, DNG, SNG, mu negative, zero index?
So dispersion curve, what he or she meant signifies. Yeah, right. Actually, without knowing the frequency of your interest is located, whether it is located in the beta negative region or beta positive region or beta zero region. Actually, for a practical antenna engineer or circuit engineer, they don't care about that. But as a metamaterial person, I had to investigate whether my antenna or bandpass filter or what power divider works at the right region I want it to have. That's the thing. To convince myself and to have a confidence.
Okay, so next is, which is better to place Metasurface on ground plane or on the above of the patch radiator? How can we decide?
Please read that again.
So which is better to place Metasurface on ground plane or on the above of the radiator? How can we decide?
Well, luckily, there are a bunch of literatures you can do some research on, like a fabric parole cavity. Then you are required to have at least two parallel plates. Two planes above the source of the radiation and below. But superstrate, you don't have to put the metasurfaces under the source of the radiation like that. So luckily, those three areas are well divided. But in the past, when I had a regular course or program in Korea to teach engineers and students or professors on metamaterials, there I showed them this can be actually, we wanted to increase the directivity of the antenna. The antenna itself is a very simple patch antenna. We could put the superstrate. At the same time, the back was kind of substrate, but substrate which has air holes, or some people say it's a holy metasurface. So by putting superstrate above the antenna and under the antenna, and by combining and optimizing the locations of the air holes and the sizes of the air holes, in the hosting materials, we could increase more the directivity antenna on the basis of the good impedance match and good refractive index match like that.
So the last question, can you explain the physics behind RF interface and BGA or IC interface? You know, metallic connecting lines may obstruct microwaves.
Read that please, again.
Yeah, can you explain the physics behind RF interface with BGA interface or IC interface? Do you know metallic connecting lines may obstruct microwave?
Oh, so the metallic wires in the kind of RFIC, yeah, metallic wires or in the RFIC can obstruct. What did she or did he say? Obstruct?
Yes, sir.
Obstruct the propagation of electromagnetic wave kind of thing, right? Am I right?
Yes, yes sir.
Yeah. We want to avoid unnecessary wirings where the electromagnetic fields have to go, because but the wavelength is much larger than the width of the metallic wires. Actually, sometimes we don't care, as you see. So, it's a kind of a relative matter if the wires, but the wires are very thin or thinner, much compared to the wavelength of the fields we want to shine or pass. Then one line or just a couple of lines, that's fine from my experience. But the what wavelength of your what interested frequency and the width are quite comparable. Width of the wires are quite comparable. Then, as you see, you can expect some reflection from the wires, and reflection also causes the poor impedance matching of the what digital circuit like that. So, but that depends upon the polarizations of the fields, how the fields are generated inside of the RFIC. But if I'm saying simply what the frequency or wavelength of the EM fields and the sizes of the wirings or some lines should be taken into consideration. So the wirings should not work as kind of a coupling structure or kind of just obstructing just reflection structure like that.
Yes, sir. One more last question is there. What should be the thickness of the metamaterial absorber along so that incoming calls signals don't attenuate?
Singles what?
What should be the thickness of metamaterial absorber along so that incoming signals don't attenuate?
Attenuate or propagate. The last word is what was that?
Attenuate. Incoming signals don't attenuate.
Don't attenuate.
Yeah.
So the thickness of the absorber, maybe that is the total thickness of the absorber, I think, because absorber consists of some layers, right? Such as a Salisbury or Salisbury absorber, as we have seen a lot. Attenuation usually occurs even within the lambda over 4, such as a 0.25 lambda of a frequency of the interested frequency. So inside, what usually no, yeah, several layers. The total thickness maybe yeah, just less than quarter wavelength. Then the attenuation starts. But the attenuation actually is caused by the multiple reflection within the surface of the absorber and the metal backing. And the absorber surfaces are usually going with the, what is it? Resistors, right?
Yeah. Sir, one more question is there now. How we classify the metasurface in transmittive type or reflective type?
Yeah, that depends upon your final or high-end objectives. And so, but just transmittive and reflective. Actually, reflection all the time should have at least some kind of obstructing termination, but transmissive or just a transmitting structure, even though it is within the dielectric material or it is within the composition of the different materials, actually layer by layer or interface by interface, impedance matches impedance match between these different layers should be guaranteed. Then energy doesn't come back and it is transmissive. But if you at least put or insert different impedance, then the incoming EM wave starts to reflect back, then it is called a kind of a reflective type.
Yeah, one more question is, any other material can be combined with metamaterials as absorbers for better performance?
Correct. Yeah, I could pick a question from the chatting window. There was a carbon. So carbon can be one of the quite cooperative materials which go with the just a Teflon meta pattern layers. Carbon or glass. Glass can be working for you too.
Okay, I thank Professor Kahng for such a vibrant talk and for answering all the questions received in the chat box. And you have started from the introduction to 5G, and then what about the metamaterials, dispersion curve. So nicely you have explained the metamaterials with including metasurfaces, beamforming, 5G and WBAN, metamaterial circuits and antennas for 5G communication, MIMO, zero order reference antennas, and different design approaches. So I thank you, Professor Kahng, on behalf of IEEE Rajasthan subsection, IEEE APS chapter, Government Women Engineering College, and MNIT Jaipur. Now, Professor Sharma is there to say a few words.
Yeah, thank you very much. It was a very vibrant lecture.
Thank you.
Lecture which we have delivered it, and I hope that the researchers will be benefited. Yes, all the queries which they have raised, and I wish to meet you again very soon.
Definitely.
Is over.
Yeah, I appreciate you for inviting me. That was my pleasure.
Yeah, thank you, sir. So we also enjoyed your talk too much.
Yeah, thank you. And I'm going to enjoy the rest of the talks and this seminar.
Yeah. Sure. You're always welcome.
Yeah. Can I say goodbye?
Bye. Okay, bye. Sir. Bye, sir.
Yeah.
Okay, participants, we will meet again at 2 p.m.
Thank you.
Yeah.
For the
Have
talk
a good
of
one.
Professor Filippo Costo.
Good luck.
Okay, thank you. Thank you.
Thank you, Sanjeev, for organizing all the beautiful meeting. Thank you very much.
Yeah, thank you, sir.
Thank you.
Save करो उसको topic. Okay, thank you, sir. वहाँ पे ऊपर है stop recording करके उसके बाद पूछेगा